So can you see my slides?
Yes. Yeah.
Okay, and it will work smoothly, right? Okay.
Yeah. Very smoothly. Yeah.
Okay, great.
Looks good.
Mhm.
Okay, good. I will start to chair this session. Okay,
Sure.
so hope everyone have a good rest and be prepared for this session. We have four
Mm.
speakers. Each speaker will have 30 minutes, including questions. And after that, we have 1 hour discussion, and it will be good if like the speakers could stay, for a discuss session. Okay, so our first speaker is Professor Tongyang Li. Tongyang is assistant professor at Peking University. He obtained PhD degree at the University of Maryland and also did his postdoc at MIT. Where Tongyang has done lots of nice works on the interdisciplinary topics among quantum computing, machine learning, and theoretical computer science. And we're very honored and pleased to have Tongyang speak here. And I'll hand it over to Tongyang. You can start. Yeah.
Yeah, thank you, Xin. Thank you. Thank you for the very nice introduction. Hi, everyone. My name is Tongyang, and today I'm happy to introduce our recent work on QCircuitBench, a large-scale data set for benchmarking quantum algorithm design. So this is a joint work with my PhD student Lei Zhang, Wang, and also my collaborators Yuntian Gu and Ithaca, and actually we are all in the Peking University. And this is actually a work accepted by NeurIPS 2025 that just happened. I mean, I think last week in San Diego in US. So it was a paper in the dataset track in a dataset track of that conference. Okay, so let's get started. So the head of intuition of this work, and in general, as I guess you probably noticed that it's just AI is developing so fast. And I think a very important direction, I mean, after we have this kind of large language models for natural language processing, also I think like in general, in like the multi-modes of AI, for instance, about like vision, about graphics, about, for instance, like music or just about sounds in general, I think has been developing very fast. But I think in general, I think people, I mean, when we want to do AI research, I mean, as a whole, I think the direction for AI for science is very important in general about that actually we want to improve the capability of reasoning and improve the capability of solving some important, I mean, real world problems, right? So in general, I think the research for AI for science is probably not only relevant of relevance to, for instance, the audience here, but also of great importance to just like in general people working in AI, right? So for instance, one of the very famous example is the AlphaFold, which actually, I mean, predicting the structure of proteins and actually was a Nobel Prize result. And also, I mean, beyond, for instance, like biology and chemistry, that actually for instance, we predict actually the structure of proteins, or maybe the, for instance, like structure of molecules in chemistry, etc. I mean, starting from I mean, I think maybe 1 or 2 years ago, I think we also been trying to understand, okay, for instance, can I solve math problems in a good kind of sense? Plus math represents, I mean, I think probably the most reasoning part of the science, right? So there is an important result called alpha proof that actually achieved like a similar, sorry, like a similar level of like a silver medal result compared to the International Mathematical Olympiad competition, right? So this, I mean, is a combination of formal like the input is some formal problems, and actually, I mean, we use like silver network to get some formal proofs, and it's basically like silver medal kind of capability. And I think this year is basically reached the gold medal of the IMO competition, right? So those are basically, I mean, people some exploration for AI for science. But as you can see, for instance, this results is actually based on like basically formal verification. Also, a very important framework in math called Lian that actually, I mean, gave like formal proofs of mathematical theorems, right? But I think it's probably, I mean, more like, I mean, accessible to like general people working AI is probably that. How about actually, I mean, we just talk about, I mean, what is the capability of which we just use large language models for solving math problems. And there are actually, I mean, some exploration along this line. I think I think very, very early, maybe like 5 years ago, I think there's a famous paper just this called automatic theorem proving that just use this kind of, GPT-based large language model to prove theorems. Later, there are also some other large language models, for instance, like the DeepSeek model in China that actually talks about, okay, so how we can do just formal mathematical reasoning by their large language models. And actually, there are also a very important result, I think, by Princeton called the Godot Prover V2 that actually, okay, so it seems that actually like their interaction between like formal verifiers like Lian and also just large language models can actually, it's more like we have a bootstrapping of the prover that actually can give good results of proving theorems, right? So those are just some kind of explorations in AI for math, or in particular large language models for math for reasoning. But I think that the point is that what if actually, we want to use AI to enhance the behavior of quantum computing, right? So this is actually, something that is probably more of relevance to this specific workshop. And I think we want to think about, what is the difference here? And in particular, I think quantum computing is more like a task of algorithm design that actually you want to design algorithm that can achieve quadratic to super polynomial speed up. And also on the other hand, I would say that actually just quantum algorithm is actually quite different compared to classical algorithm. So maybe you want to understand, okay, so what if actually we just use large language model for algorithm design? And in particular, what is the current capability of using large language models for quantum algorithm? Are they good on this? Are they bad on this? I think we want to have a good understanding about this in particular. Okay, so this is basically our work is actually aiming at, and actually we call this work as a QCircuitBench. So this QCircuit just represents quantum circuit, and this bench represents that actually our result is more like a benchmarking data set, right? So I would say that actually our main contribution, if we make a summary here, is that actually our work is the first large-scale benchmark for AI-driven quantum algorithm design, right? So basically, for this data set that actually we use to benchmark the behavior of quantum algorithm design by large language models is that basically, for the task formulation side, we have actually a carefully designed framework capturing the core aspects of quantum algorithm design. In particular, basically, we have 3 task suits, and actually, in general, we cover like 25 types of algorithms, right? And in general, I think this is covers probably most quantum algorithms that actually we can think of. And in terms of the data points, I think it's like basically, I think this is like 120K data points, right? And supporting in general, a lot of different kinds of algorithm implementation. Yeah, so also very importantly, I think basically, in general for AI, among AI for math and large language model for math, I think it's very important that actually, we include some kind of, formal verification that actually we need to verify that actually our result is actually correct or not. So basically, like in terms of just writing down the codes, I think we have built-in validation tools, basically enabling us to actually check our result is correct or not. And also, I think our work, I would say as later, I will explain the experimental results. It's definitely more on the side of a benchmarking data set. But also, I think this data set is probably has some training potential and demonstrates promise as a training set. We have preliminary fine-tuning experiments. Okay, so let me introduce more details on this. So if you think about, okay, so I want to benchmark large language models using quantum algorithm design. What are the challenges here? So I think in particular, if you think about this, okay, so just quantum algorithm, it's typically written down by quantum circuit. But for instance, if you want to test, the behavior of large language models, shall we use, for instance, natural languages? Or maybe we want to use math formulas. So the good thing, for natural languages, that is very easily, accessible, but in general, it can be verbose and also ambiguous. For math formulas, it can be precise, but in general, we need to think about how to, formally verify this. So this is probably something we need to be careful with. And also something that is, a little bit special in quantum algorithm design compared to classical algorithm is that typically, a lot of quantum algorithm, we assume a quantum oracle. For instance, in Grover's algorithm, we assume an oracle that actually which place is marked. They are just in general, quantum oracles exist a lot in quantum algorithm design, right? So we probably need to think about how actually we want to make, construction of the oracles, right? And also, a lot of algorithm that actually is not only a quantum algorithm, but after we do some measurements, there are also classical, post-processing steps, right? After we get some measurement results, how actually, we can understand this result. For instance, in Shor's algorithm is probably just, the period finding is just one of the steps, but how you understand the period finding result, and actually, you probably just you need to do some basic number theory about how does that work. So this is also something we probably need to think about, right? So basically, the design principles, I think, in our quantum data set is that basically we try to address these challenges, right? So for the formulation part, basically our solution is that we see this more as a code generation perspective, that actually we just represent quantum algorithm with quantum programming languages, right? So in general, okay, so I mean, of course, I mean, there are different quantum programming languages, but the baseline we use is actually, we just follow the IBM's Qiskit, this kind of language. I mean, both, I mean, just for the standard, I mean, Qiskit language, and also, I mean, for the assembly level language, we use the OpenQASM, and also based on IBM. Right. So for the oracle paradox, I think the thing we actually do is that, I mean, for our oracle-based quantum algorithm, the thing that actually we do is that actually we have a separate oracle library that actually preserve a black box oracle abstraction value in labeling compilation that actually in OpenQASM. That actually, okay, we treat this as a separate file that actually, okay, I need to, I mean, construct, for instance, oracle that actually, I mean, for instance, like for the Grover's algorithm, mark the specific place and do not mark the other places. Actually, I have a separate file that actually, I mean, do this kind of oracle construction. And actually, when the algorithm is calling this, I mean, I just treat this, I mean, just as an interface, but actually this is more seen as a black box, I mean, on our current code, right? So this is actually, I mean, we just do a separate, I mean, oracle construction library. And for the classical procedure is that basically after that, of course, we require some post-processing on functions, I mean, including, for instance, the number of trials to characterize query complexity, etc. Right. So those are just, I mean, in general, some design principle. And I think maybe this is probably the time that actually I bring to you together what is actually, I mean, the data set and actually how does the thing look like. So for instance, maybe you think about this. Okay, so for instance, maybe we go back to like 20 years ago, we think about how we actually make a data set for classification like we do the Avnis data set. So you just have cats and dogs, right? I think it's not that difficult that actually you make some data that, for instance, maybe you just go to like a places where there are a lot of, I mean, cats and dogs. You just take some random pictures for them and actually you just mark them. I think making data in general, I mean, making some data is in general possible, but making a comprehensive data set and actually make this helpful in general, I mean, that actually we have not the necessary parts for AI and for benchmarking, for training. I think this is something we probably need to be carefully thinking about. So in particular, our QCircuitBench framework is actually composed of the following part. So I mean, maybe let me actually explain this to you one by one. So the first part is basically the problem description. So for the problem description part, we definitely, we have natural language part. So I mean, you can see this data set. I mean, each data point actually both have the part of natural languages and also have codes, right? I mean, as you can see, there are actually some Python code, Qiskit code, etc. Let me actually explain this one by one, right? So for the problem description, I mean, we have carefully handcrafted prompts that in general is actually composed of natural language and also, I mean, LaTeX math formulas. I would say this is more like an interface of quantum oracle and composite case. And for instance, maybe this is just like a natural language part for the Simon's problem. And in general, I mean, it's more like what actually you probably just check a textbook is probably looking like. But in general, I mean, for the problem description part, I mean, all the parts are actually highly standardized that actually, I mean, they have similar structure and also have similar math descriptions, right? So this is about the part of problem description. And next is the part of the data creation part. So this part, basically, we just create a data set from scratch. And actually, I mean, we just generate primitive quantum circuits and actually we extract circuit definitions, validate the data points, create a benchmark pipeline. And it's basically a Python code in terms like this, right? So basically, I mean, it's still, I mean, a very high level and actually, I mean, just like standard, like Python code. But actually, we can use this to generate, I mean, a series of data. And after that, we have the Qiskit part. Okay, so we have this kind of Python code that actually generated a lot of the data. Then basically, we then create quantum circuits for algorithms of different settings, right? So basically, I mean, we have this kind of, I mean, Simon circuit, and actually, I mean, for instance, the Simon's problem on N-qubits. But after that, I mean, for N-qubits, I mean, the highest string, it can be, for instance, like different binary strings, right? I think in general, we want to have different, I mean, like instances for the problem. Right, so this is basically about the generation code. And after that, I mean, for our algorithm circuit is actually composed of OpenQASM files. And in general, just look at like very standard, I mean, quantum circuit. This just means that actually, I mean, we on the first qubit. I mean, it actually marks qubit from the zeros, I mean, to the first, second, etc. So this is just, I mean, we have H gates on the first, second, third qubit. I mean, we do an oracle to H gate, I mean, etc. This is just very easy to understand. And actually, this is just, I mean, I would say it's just assembly level language OpenQASM that actually, I mean, directly, I mean, you can translate from the IBM quiz code to the OpenQASM code. And after that, I mean, for the problems with oracles, we also have an oracle. We also have an oracle definition. But this is, I mean, again, it's a separate file that actually, I mean, if you need to mark a specific item, or if you, for instance, I mean, you need to use the oracle to encode some information. I mean, we have this kind of oracle separately. And after that, I mean, a very important thing I think is probably more like coding heavily in this project is actually the post-processing function. Actually, I mean, for each of the different tasks we write down, I mean, like a specific post-processing codes that actually, I mean, we understand how actually, I mean, we do the post-processing that actually, okay, so I have this kind of measurement result, and actually, okay, does this actually, I mean, satisfy, I mean, our algorithm design tasks, etc. So this is actually, I mean, about the Python code. And also we have a case test that actually we need to evaluate and implement algorithm. And actually, I mean, we have different scores, as I will later explain in the experiment part. All right, so this is basically about the construction of the data set. I think for the task suits, I think in general, we have three task suits here. So we basically cover oracle construction. That actually, okay, I have an oracle, and actually, for instance, I want to solve the Grover's algorithm. I need to have such kind of oracle, right? So we have a task for oracle construction, and of course, we have task for quantum algorithm design, and this basically covers textbook level algorithm to advanced applications. And also we study random circuit synthesis. So actually, okay, so for instance, I mean, I want to have a specific output. I mean, basically you can treat this as a quantum state preparation problem. And actually I have a bunch of gates from universal data set. How do we actually need to make this kind of circuit synthesis task? Right. So basically, I mean, for the quantum algorithm part, this just covers the textbook results. And I think we also try to cover something that is, I mean, interesting. For instance, I mean, that is actually, I mean, not so textbook, but it's still helpful going for us to actually test the behavior of the result. So in particular, we include like an algorithm called the generalized Simon's problem. Whereas I think you can probably understand that actually most quantum algorithms we've been talking about, I mean, especially on discrete domains, we typically just talk about Boolean domains. But I think, for instance, for the Simon's problem, I mean, there is previous research on that actually we talk about not binary, but in general, binary, I mean, basis. And actually, I mean, in this kind of, I mean, for instance, we can go from binary to trinary. I think in our experiments, we just do the experiments where p equals to 3 on trinary basis. And actually, I mean, we want to understand, okay, what is the behavior of this kind of generalized Simon problem? I think for our understanding, if you have a basic understanding about quantum algorithm design, this kind of generalized Simon problem should be not too difficult to actually move from binary to in general p-array strings. But it actually turns out to be very difficult. I mean, for large language models, as actually we were going to see. But actually, I mean, for the circuit synthesis part, we in general talk about quantum information protocols like GHC state preparation, WC preparation, etc. I mean, for a lot of quantum information tasks. And also we cover some variation of quantum algorithms. Okay, so I think this is basically, I mean, the dataset framework, and let's actually here talk about experimental results. So the benchmark pipeline is actually working like this, right? So we talk about the QCircuitBench dataset that actually, I mean, we have the problem description, algorithm, or oracle circuit, and also, I mean, if necessary for algorithm design tasks, we have the post-processing part. So basically, I mean, you can treat this more as a few-shot learning. So we have some experiments on one-shot learning that actually I just tell the large language model one example. Okay, so what is the question? What is the answer, right? So I mean, this is called one-shot. So we have different experiments, and actually sometimes it's actually one-shot. That actually, okay, so we just give one examples on this. For five-shot experiments, we just give 5 examples on this. And actually, I just put this into like some common large language models, for instance, like the GPT, like the Llama by Meta, and also I mean some other models, right? And also like Q and DeepSeek, etc. So basically, I mean, we just test this on this result, and basically we have the verification function, and also I mean we test the semantic scores, etc. So in general, we observe that the experiment results. Let's actually take a look at the experiment results. It's something like this. So basically, I mean, we can have this kind of algorithm design task and oracle construction, etc. So basically, I mean, you see that actually, I mean, the large language models, I mean, they have some relatively good understanding about some simple problems, like I would say Bernstein-Vazirani and Wishosa. I think the results are relatively better. But I think it's just the circuit for the Grover's algorithm is actually already getting complicated, and you see the scores for the Grover's algorithm is actually not so good, and also it's not so good for the Shor's algorithm. So this ternary just means we move from the binary to from p equals to 2 to p equals to 3 for the generalized Simons problem, you see the score here is actually not so good, and actually for the oracle construction part, it's basically like 0. So it's in general actually quite challenging here. I think I would like to mention that actually for the models we were using here, actually, I think we did experiments like roughly speaking like a year ago. So it's actually not actually the state of the art large language model. Like the GPT is still like the version of GPT 4.0. I think for Q1 is currently Q1 3, but we use Q1 2.5. And actually, I think like DeepSeek, they have, I think very recently, early this month, they have a new model, etc. But I think for the models we use are actually, the state of the art models like a year ago. And actually, those are the results here. I would say, relatively speaking, I think you see the scores. Here, I think for the dark color is basically, we use the GPT-4, and then for like the green color and actually the light green color, I think they represent like Q and DeepSeek, etc. So, and also I think the metas, the Llama 3 models. So I think the behavior of the GPT-4 is, overall, I think it's slightly better than the other models. But I think there are also some tasks, like for instance, you see the QAA here, you see the VQE here, that actually the DeepSeek model is actually really good. I think, for instance, like state preparation problem, I think the QM model is relatively good. I think if you see the average score, I think it's probably the GPT-4 is the highest, but by a little bit margin. But it's just the behavior of different large language models, on different problems are actually a little bit different. So this is basically about the blue score experiments, the measure similarity between model generated output and reference codes. And also, for the verification score, so actually, okay, we have this kind of post-processing functions. And also, this is actually a result that actually, we have human evaluations. So actually, we just ask some people knowing quantum algorithm design, perhaps some PhD students that actually just write down the codes for these problems. And I think it turns out that actually, I think these are just more like early career, like PhD students. They probably just have a good understanding about like textbook level quantum algorithm, but maybe not like quantum algorithm design research. But it turns out that actually, the human score is actually, better than all the large language models. I think probably the best, is the GPT-4 with 5 shots. I think it makes sense actually for the large language models, if they see more shots, that actually their score should like intuitively should be higher, right? But I think none of them is actually as good as the average score of just human understanding this knowledge and write down the codes. Right. So basically, in this, maybe let me actually, I think I probably need to be a little faster here. Okay, so in general, for the observations here, we have found, like in general, as I just mentioned, the few shot experiments is actually better than the one shot experiments. And like GPT-4, excels in general in context learning and long code understanding. But harder tasks, for the comparisons between different models, this is in general a little bit, like each models have their pros and cons, right? I think also something that is interesting about like basically the current capability of large language models is that there are some specific error types that actually we observe, right? For instance, the first error type that actually we observe is actually the improvisation error, right? So sometimes like GPT-4 can use unsupported like custom features, custom failures, when compiling the code. So for instance, if you see this kind of code, I think this is very, very intuitive and understandable. But one issue that actually, if you put this into the open custom compiler, is that actually it does not support a for loop, right? Because actually, after all, I think when we write down, quantum circuits, having like a for loop, a while loop, for this kind of like gate, it's just, having a series of, C0 gate that actually, like controlled between actually the I-1's qubit and the ith qubit. This is very intuitive, but I think in general for quantum algorithm design, if you have this kind of for loop and while loop, it can be tricky at some places, and actually having this kind of for loop, it was, not actually, supported in the custom version that actually we use, and actually that is the reason why it actually called a failure. But it's just a GPT-4 use this kind of, like for instance, like classical programming language perspective, and use the for loop here and actually make the thing wrong here. And also, the improvisation error that actually happens is that, typically, you see that actually when people, human write down, open custom code, we just use, for instance, actually, the Q0, Q1, Q2, etc. to represent the qubits. But here, something that is very tricky is that, for this code, actually, it has an overload issue that actually it calls a qubit an X. But the X, in custom means the X gate in general. So this is actually overloading and actually just, it just have this kind of error, when compiling the code, right? So this is actually, the improvisation error that we observe that actually, when large language models, they actually, they try to solve the problem, they will have this kind of issues. So the second kind of error is basically called counting error, right? So in particular, I mean, there is a famous, I mean, hard instance for large language model is to count the number of R's in the English word strawberry, right? So here, I mean, we observed a similar phenomenon that actually, I mean, in general, large language models cannot very easily to characterize, okay, so for like binary string problems, like Bernstein-Vazirani, to identify the zeros and ones in the secret string, right? So for instance, I mean, for instance, assume that actually we have a Bernstein-Vazirani instance about when n equals to 6, and actually the secret string is this 0, 0, 0, 1, 0, 1. And actually, it tells us that actually, okay, the bits that actually equal to 1 actually found in index 2 and index 5. But no matter, I mean, sometimes, I mean, like the codes, I mean, raised from left to right, sometimes raised from right to left. But I mean, in either case, I mean, the ones are actually at the index 2 and index 5. And actually, just, okay, it just understand this at index 2 and index 5 and actually give a circuit like this. I mean, the qubit 2, qubit 5, and of course, this is going to be a round circuit, right? So it's just, I mean, very difficult for large language model to identify, I mean, the positions of zeros and ones. It's probably just because, I mean, the tokenization way they use is actually, I mean, not actually, I mean, just use like the zeros, ones, I mean, in human. But I mean, in general, I mean, I think this is a very common mistake that is currently made by the large language models. And also, I mean, we can observe that actually, I mean, another type of error is basically data contamination. And actually, this brings us, and also I think brings the why actually having this kind of, I mean, data set is actually important. It's basically because the LLMs typically they just call, for instance, like Qiskit tutorials. Of course, I mean, like with IBM, they actually make Qiskit. They need to write down tutorials and they need to run, for instance, okay, for specific n, what is the like the circuit for that? So typically, I mean, like the GPT-4, for instance, I mean, like I think basically in their tutorial, the binary string they use is probably something like 10101 here. Then the circuit is, I think is going to be perfect. But I think if you change the string, for instance, not like 10101 to something like maybe 11000. I think they keep answering the circuit basically for the same string. Sometimes you will observe this. So they see like the content online that actually you can see the Qiskit tutorials. And actually, I mean, for n equals to 5, I mean, basically the looking of the Bernstein-Vazirani algorithm, okay, it looks like this. But actually, if you change the string here, it keeps answering that. And actually, this just, I mean, makes us understand, okay, so this is actually more like a data contamination. And that actually makes why our work is important. Actually, for the same n here, we generate different, I mean, like data that we can hopefully have like large language models and also other AI models to learn quantum algorithm design. I think I'm actually running out of time soon. So I think we basically do some fine-tuning results and think the fine-tuning results, I mean, demonstrates that actually, I mean, the task is actually getting better. Definitely, especially for counting the one bit, like the problem that actually, okay, so I have, I mean, like all these kind of binary strings and understand what is the binary string. So basically, I mean, we just do like just standard LoRa-based fine-tuning. We need to do this on open source model. So we just do this on Lemma 3. And it turns out that actually the fine-tuning result is actually, I mean, relatively positive, but there are still some difficulties. There are some minor signs that actually, I mean, the fine-tuning is actually not working that well. But actually, I mean, this is probably some direction we want to work on, hopefully can help improve the capability of quantum algorithm design by large language models. Okay, so I think let me give a very brief summary here. So I think the takeaways here, so the novelty of this work is that actually I think our work is the first large-scale benchmark for large language model quantum algorithm design. And I think basically the data science design task is more like from a perspective of code generation. And actually we also have automatic verification functions. And also you can see we have this kind of model and extensive data structure. And also experiments, and actually like we all observed that actually, I mean, QCircuitBench poses significant challenges to current large language models. And in general, fine-tuning experiments demonstrate early promise. And I think we need to further explore along this. And also there are definitely some open challenges about data bottleneck, about fine-tuning for design. And I think in general for evaluation benchmarks, I think there are also a lot of directions we can probably think about. Okay, thank you for your attention. Yeah, any questions?
Very nice talk. Any questions for Tongyang? And I have a quick question, like,
Sure.
how have you tried like this kind of benchmark for there are lots of like quantum information protocols,
Right.
like super dense coding teleportation, but somehow like easier than quantum algorithms, these kind of basic ones. Have you tried this kind of thing?
Yeah, definitely. So I think I didn't, I mean, I have time to explain that, but I think I do have a page of slides to cover that. I think in general we have 25 classes, and those definitely cover like teleportation and super dense coding. Yeah, so
I
it's
see.
basically, I mean, backbone information protocol. So this is more on the past that
Oh.
actually we like put this in the task tools of random circuit synthesis. I probably should change not to random circuit synthesis, but in general about like circuit synthesis, actually, I mean, whether for this circuit, actually we can, because after all, I mean, for like the quantum teleportation, it's more like you have an input state, and actually, I mean, this input state is probably on the other side prepares a specific state. You want to actually, I mean, on the Bob side also prepare the state. So we treat this more as a circuit synthesis task, and actually, I mean, yeah, we do some experiments on that.
And from your results, like what kind of task will be like more difficult or challenging for large language model?
Well, I would say that actually the best is just, I mean, the various, I mean, because I think the Bernstein-Vazirani problem which shows an algorithm, the algorithm is very simple. It's just, I mean,
I see.
like a layer of H, the oracle and a layer of H. So Bernstein-Vazirani which shows that they are the best. I think basically on large language model understand them very well. I think the next tier is basically more like probably Simon's problem. And I think my intuition from what I remember from the experimental results is like for state preparation tasks, and also, I mean, the next year's Simon's problem, because I mean, after all, like the circuit for quantum teleportation is not very difficult. And I think also super dense coding, and also like GC state, they're relatively simple, but they're not as simple as BV and also the Duish-Josa. So I think the result is okay, and you can see larger models can have good behavior, but I mean, it's far from perfect. And it's basically, I think it's not very good. I think it's about Grover's algorithm, about Shor's algorithm. Probably is more complicated than for our test case of general Simon's problem. I think there are like a research paper on this, and actually it was not a very high cited research paper. It's more maybe like cited like maybe 10 times or so, because it's relatively straightforward generalization. But it's more like a new problem for large language model. You see actually the result, I mean, for general Simon's problem is really bad. So I mean, it's probably something new is still going to be very challenging for large language models. So I think for information protocols you ask it's okay, but I mean, not perfect, some good results, but I think it's probably just like in the middle.
Okay. Yeah, thanks.
Yeah,
So
thank you.
any other questions for Tongyang? Okay, so we'll leave time for more like discuss sessions. Okay,
Sure,
good.
sure. Yeah, thank you,
Sure.
Xin.
Yeah. Thanks, Tongyang, for a nice talk.
Yeah,
Okay,
let me end screen share. Okay.
okay, and we'll continue. And our next talk is Eric. Are you there?
Yeah, let me share my
Cool.
screen.
Okay, so Eric Anschuetz is a Berkeley Fellow at Caltech, working on the algorithm implications of spin glass theory, and he has done amazing works on quantum algorithms and quantum machine learning. And we are very happy to have you here. And I'll hand it over to you. Yeah, Eric, you can start.
Thanks for the very nice introduction. Also, sorry about my lighting. This is all the lights in my apartment, and it's still pretty dark. So I am here.
Yeah, we can see.
Anyways, yeah, today I'm talking about using glassiness to understand when quantum thermal states are easy or hard to prepare. So what I'm talking about today is based off these two papers. Um, the second one was done in collaboration with Alexander Zlakapa at MIT and also Bobak Kiani at Bowdoin. So shout outs to them. All right. So these two papers were really motivated by trying to answer the question, what makes Gibbs state preparation hard? And okay, so for kind of technical reasons, I'm not going to specifically talk about Gibbs state preparation in this talk, but really mostly talk about what makes optimization hard. So in some sense, optimization is an easier problem than Gibbs state preparation, because if you prepare a Gibbs state at low temperatures, of course you can prepare, that's one example of preparing a low energy state of a quantum system. So in some sense, optimization is an easier problem, and it's also easier to talk about in a talk. But whenever I say optimization, you can also think of Gibbs state sampling, and I think everything I say in this talk will hold true as well. Anyways, before I answer this question directly, I first want to have a brief aside and talk about why complexity theory can often often be misleading when talking about optimization and sampling problems. So to do this, I'm going to talk about one of the canonical examples of an NP-hard optimization problem, which is max-clique. So if you've somehow never heard of this before, essentially the problem we're given is, given some graph on n vertices, so here's some graph on 6 vertices, we're trying to find the largest clique. So the largest maximally connected subgraph of this given graph. So helpfully, I've highlighted the answer here already for this graph. If you couldn't figure it out, it's 1, 2, 5. But more generally, as this scales up to larger and larger graphs, this becomes a very hard problem. And, not only is it believed to be hard to optimize exactly, so to find the, literal exact maximum clique size, but also to even approximate. So there's this famous result in complexity theory known as the PCP theorem. And one of its implications is that if you try to approximate max clique to some approximation ratio that's only slightly better than trivial, it's still NP hard. So, to understand why this is only slightly better than trivial, whatever graph I give you, the max clique size is only at best going to be n. That's the number of vertices in the graph. So that's as big as the max clique can be. And if I just have an algorithm that always outputs the vertex 1, that's an algorithm that always achieves an approximation ratio of 1 over n. In a very not interesting way, it just outputs, it's a constant function. It just always outputs 1. And this theorem essentially says that you can't do much better than that. So this algorithm that's really dumb achieves 1 over n, and it's really hard to even achieve 1 over n to the 1 minus epsilon, at least in the worst case. But okay, let me now get into why this is somewhat misleading in terms of how this applies in practice. And that's essentially because for these worst case hardness results, at least in complexity theory, these are for adversarially chosen examples. So we could also ask, how hard is this problem if we're just given like a typical graph from some ensemble? So for instance, what we can do is consider Erdos-Renyi graphs. So these are graphs on n vertices where, let's just say for concreteness, the presence of an edge is chosen IID with probability of half. So, for most graphs, roughly half the edges are going to be there and half of them aren't. And each edge is chosen IID. You can use something called the Paley-Zygmunt inequality. It's some standard statistical inequality, and show that with high probability, the maximum clique size over this distribution of graphs is something like 2 log n. So in other words, for these random graphs, max clique sizes are only logarithmic in n instead of extensive in n. And so this example of a really trivial algorithm I gave in the last slide of just always output the vertex 1, already for this distribution with high probability, you're going to achieve an approximation ratio of 1 over log n, 1 over 2 log n. So already this is beating what the PCP theorem kind of naively would tell you about, what would go wrong if you tried to take these worst case theorems and apply them to average case instances. But actually we can do even better than 1 over 2 log n, which maybe isn't surprising given how trivial the algorithm is. So what you can do is the following. If I'm given some graph, I just pick a random vertex, and then I throw away all of the vertices that weren't adjacent to that vertex in the graph. And then I repeat this a bunch of times until I've thrown away all of the other vertices. And because this graph is Erdos-Renyi distributed, at each step you're throwing away roughly half the graph, half the remaining vertices, right? Because for any given vertex over this distribution of graphs, roughly half the half the other vertices are connected to this vertex. So you're throwing away roughly half of them at each step. And so roughly you're getting a clique size of log n when you do this. So suddenly we've gone from it's very hard to achieve anything better than 1 over n, to achieving an approximation ratio of a half over typical problem instances. Okay. So this is already like, pretty amazing that in practice for this optimization problem, we can do a lot better than you would pessimistically, expect from these complexity theory results. And I put in a little blurb here that you should also have a similar story if you're interested in sampling from the Boltzmann distribution of these configurations, where your energy is given by your clique size or whatever. So, a very similar story holds for sampling problems where you can do much better on average than you would expect in the worst case. So, okay, we're now beyond the realm of what worst case complexity theory can tell us. And so a natural question is, well, can you do better than a half? We've already blown the 1 over n to the 1 minus epsilon out of the water. We can hope potentially to do even better than a half. And even though this algorithm I presented was like 50 years old, or is 50 years old, still we can't do better than this algorithm. So some reviews call it the most embarrassing open problem in this field. I think it's a little, pessimistic. They're being hard on themselves because it's a really hard problem to try and figure out how to do better than this. And in fact, it seems impossible to do better than this using efficient algorithms. So, okay, how do we, well, first let me kind of say what this kind of represents. So these kinds of problems exhibit what are known as statistical computational gaps. So that's just a fancy way of saying that statistically, we, I mentioned this Paley-Zygman method a few slides ago. You can compute what the exact, at least in the large graph size limit, you can compute what the exact max clique size is just using math, with high probability. But computationally, we don't know of any efficient algorithms that actually give you an example achieving that maximum. So for this reason, it's called a statistical computational gap. And over the last decade or so, a pretty rigorous and complete theory of these statistical computational gaps has kind of come about, motivated by the physics literature. So in the classical literature, it's called this overlap gap property, or in the computer science literature, I should say. But I think physicists would call it a spin glass transition. So, okay, how can we understand this more mathematically? So let's say we're given some energy function over some distribution of functions. And for now, I'm going to stick to the classical setting. And then essentially what these two results that I'm talking about today do is they extend it to the quantum setting. So, but first let's talk about the classical setting. So we have some energy function, and we're interested in finding, just for simplicity of talking about approximation ratios, I'm going to be maximizing everything here, but you can turn everything into minimizing if you'd like. But I'm interested in finding a bit string that maximizes some energy function. And I can consider the space of high value points of this energy function, or high energy configurations. So the set is the set of all bit strings that achieve some approximation ratio mu of the optimal energy. And this is a random set that depends on the instance drawn from your distribution. And I can define something called the overlap gap property, which is essentially just a statement that if I looked at the set of all configurations that achieve a high energy with high probability, given an instance, if I look at the set of configurations that achieve a high energy, they exhibit some kind of clustering property. So in other words, if I look at the pairwise Hamming distance between these high energy configurations, there'll be either configurations that are closer than some nu 1n in Hamming distance, or they're further apart than nu 2n, but they're never in between. There are no configurations that are between nu 1n and nu 2n for some absolute constants nu 1 and nu 2. So if you were to plot this, it's essentially just a statement that you have like a clustering phenomenon in your high energy space of configurations with high probability over this distribution. And, you know, a lot of you are probably more familiar with machine learning. And another way to kind of think of this is as the discrete optimization analog of having terrible local minima in an optimization landscape. You can imagine if you had terrible local minima or local optima generally, and you took a cross section of your landscape, it would look similar to this. You know, you would have these local optima that are separated by, these wells essentially. And this is effectively the discrete optimization analog of that. And one nice property about the OGP, this overlap gap property, is you can actually prove rigorous hardness results without having to rely on complexity theory assumptions. So to get into that very briefly, you can also consider this ensemble version of the overlap gap property, where now I'm looking at correlated instances of problem instances. And then I say an ensemble satisfies the ensemble overlap gap property if I have the OGP even over, these potentially correlated instances drawn from this distribution. And you can see why this obstructs algorithms. And the reason is if you have independent instances, you can imagine that your high energy configurations are, generically going to be far apart if you just draw two independent instances and look at their high energy spaces. And because of this ensemble overlap gap property, you can also show that, if I have two configurations and two separate clusters because they were, initially drawn independently, and I interpolate to the same instance, because they start in separate clusters and because I have this ensemble OGP, there's never going to be a point in this interpolation path where these two clusters come together. So in other words, any algorithm that's correctly preparing high energy states along this interpolation path has to be able to jump this gap in configuration space, even under very small changes in the input, because I'm doing this interpolation continuously, imagine. So in other words, what this OGP obstructs are algorithms that are, the technical term is stable or Lipschitz continuous under changes to their input. So if I have an algorithm where if I change the input a little bit, the output doesn't change so much, then I'm unable to jump this gap along this interpolation path, and therefore it's unable to prepare high energy configurations for these models. And then very briefly, you can also show that this overlap gap property implies what physicists call a dynamical spin glass transition in these models. So if you look at the Boltzmann distribution for these random models, you essentially have some temperature where it shatters into a million pieces. It's also called the shattering transition. And your measure splits up into exponentially many clusters. And you can show that if you start from one of these clusters and try to run like a Gibbs sampling, in the classical setting, like a simulated annealing kind of algorithm, it's going to take exponential time essentially to escape from one of these clusters because you have to jump an extensive gap in free energy. Okay, so that's enough about. Oh, I should also say that, really you're proving things about these Lipschitz continuous algorithms, but also in practice, this OGP matches the performance of every efficient classical algorithm we know. Because, if you knew how to design a non-stable algorithm that could solve your problem, you would essentially have to know something about the structure of your problem beyond what these, disordered random problem instances provide. So actually, since this is from that review I had a few slides ago, since that review came out, all of these have now turned into yeses, more or less. So now, for all these examples of problems in combinatorial optimization, essentially this OGP, or a version of this OGP, tells us exactly what can be achieved by efficient classical algorithms. So, okay, that's enough about classical systems. This is on quantum Boltzmann machines, so let's talk about quantum Hamiltonians. And actually, for a while, people were trying to do this for quantum Hamiltonians because it would tell us nice things about, when can you efficiently prepare low energy states of generic quantum systems. But it turns out it's not so easy to translate the classical version of an OGP to the quantum version, or to a quantum version. So one thing you might imagine doing is, okay, let's say I'm given some Hamiltonian. I can try and reason about an OGP in terms of its eigenstates, for instance. Like, obviously, this would reduce to considering the classical case where everything is in the computational basis, all the eigenstates are. So this is maybe one potential way to generalize an OGP for quantum systems. But unfortunately, you immediately run into issues if you try doing this. Because for one, if you have two high energy eigenstates and you consider superpositions of those eigenstates, it's still going to be a high energy state. So in terms of eigenstates, it's not really clear how you would have like gaps in configuration space that you can then reason about Lipschitz, quantum algorithms for. And also when you start talking about eigenstates, things get a little fuzzy because, it's inefficient to even read out the energy of an eigenstate. So, or distinguish eigenstates in terms of how computationally complex it is. So, in some sense, it's of course going to be difficult to prepare low energy exact eigenstates because generically preparing exact eigenstates is difficult. We want some approximate version of this for it to be meaningful in any way. So, okay, that's what these two papers do. I realize I only have 5 minutes left, but hopefully I can give you a general idea of how we do this in these two papers in 5 minutes. So just very briefly, this work was motivated by a previous paper from last year where we showed when you don't have a spin glass transition, essentially. So in these two papers, we essentially talked about when you do have a spin glass transition. In this paper, we talked about when you don't. And it turns out if you have a lot of effectively Heisenberg uncertainty in your system, so if I have a Hamiltonian and I write it as a sum of terms, say a sum of local terms with IID Gaussian disorder, I can look at this measure of how commuting the set of observables is. And we showed in this paper that if this measure of commutivity asymptotically vanishes, then this Hamiltonian has no spin glass transition at constant temperature. So, right. So just to give an example of a system that's like this, the SYK model, for instance, has this commutation index vanish asymptotically. And so it's an example where you don't have glassiness at constant temperature. Okay, how did this motivate this work? Well, it turns out that up to log factors, hence the asterisk, 1 over this commutation index essentially exactly characterizes the sample complexity of learning expectation values of these observables in any given state. So if you're familiar with the classical shadows algorithm, that's what achieves this, essentially. And the sample complexity of using classical shadows to estimate expectation values of these observables is given by 1 over this commutation index. So in other words, you're not glassy whenever it's not efficient to learn these expectation values using classical shadows. Or not constant sample complexity, I should say. So this motivated in these two new papers what's effectively a quantum OGP. So in these papers, we say a Hamiltonian satisfies a quantum OGP if this commutation index is not asymptotically vanishing, and if this classical shadows estimator that comes from this classical shadows algorithm exhibits a classical overlap gap property. So this classical clustering and configuration space that I had mentioned. The kind of way to see how this might lead to a proof is that if this thing is not vanishing asymptotically, there's a constant sample complexity classical shadows estimator for the energy of a state in the system. And therefore, you can kind of translate these quantum systems into classical systems over dit strings with only a constant overhead in the number of dits you need to represent the state. So I don't have much time left, but I should just briefly mention that this quantum OGP, for instance, is satisfied by a sparsified version of the quantum p-spin model. And also, you can show that this quantum OGP implies hardness, not only for stable classical algorithms, but also quantum algorithms, which are Lipschitz continuous, and something called the quantum Wasserstein distance. So unfortunately, I don't have too much time left to get into this, but just as some examples of of algorithms which have this property, it's sort of the quantum versions of what we classically know how to rule out using this technique. So algorithms which are Lipschitz in gate complexity, whether they're quantum or classical, log n Lombardian evolution from any initial state. I also imagine if you started from a worst case state, you could show exponential bounds, but we haven't done that explicitly. VQE or QAOA at log depth, phase estimation if you're reading out log n bits of precision, and some other algorithms that I mentioned in my paper. Okay, just to quickly wrap up, this is a very formal but rigorous way of characterizing glassiness in quantum systems, and it gives us a signature of when we should expect Gibbs state preparation to be inefficient. So effectively, if you're at a temperature where you would be preparing states which are high energy or low energy, and it's at an energy that this OGP shows up, then you can't really expect to be able to prepare these states at these low temperatures efficiently. And I should also mention that it's been used since these results to look at things like DQI and other algorithms. Okay. Just very briefly, things I want to do from here are more general bottleneck theorems. So this is kind of what I mentioned with these exponential mixing times from worst case starting points. And also it'd be nice to show, as is done in the classical setting, that this quantum OGP is actually attainable by quantum algorithms efficiently, and also to look at finite dimensional or other sparse models. So, okay, with that, thanks for your time, and here are the archive links to the two papers.
Yeah, very nice talk. Any questions for Eric?
I have a question. Hi, Eric. This is Mark
Hey.
Wilde. Nice to meet you recently at QTML in Singapore.
Yeah, nice to meet you.
Thanks for your talk. It's really interesting. So I actually would like to hear about the parts that you skipped because it seemed
Yeah.
pretty important, if you don't mind. I want to
Perfect.
understand
This is
this Wasserstein condition.
Yeah. So for people who aren't familiar with this quantum Wasserstein distance, it's essentially like a quantum generalization of the Hamming distance or the classical Wasserstein distance. And without getting too much into the technical details, roughly if I have two states which differ by a k-local operation, that means their quantum Wasserstein distance differs by order k.
Yeah, so you're
Roughly.
citing the Palma paper, and
Yeah.
that's the one I remember. Is that the one that's W1 distance?
Yeah, so okay. True. This is for a W1 distance.
Hmm.
And for technical reasons, in my paper, I have to use a very slight modification of their W1 distance. It's not so okay, their W1 distance is defined in terms of some norm. The W2 distance I have to use in my proof can't be defined in terms of a norm. It's like something else, but it's effectively the same thing. Like I imagine if I could improve the proof, it would literally work for their W1 distance. But yeah, for kind of technical reasons, I have to use this modification of it that is a little bit annoying.
So does your paper introduce a new quantum Wasserstein distance?
Yeah, it does.
Okay.
So
Interesting.
unlike the W1 quantum Wasserstein distance from Giacomo and others, so they have a nice property where if they look at the quantum W1 on classical distributions, so diagonal mixed states, it recovers the classical W1.
Yeah.
That's not true for mine.
Okay.
Mine bounds the classical W2. So it's kind of annoying because it doesn't exactly line up, but it turns out to suffice for showing stability because you can think of putting, classical W2 on the left here.
Thanks. I have a follow-up question. So
Yeah.
we've been studying quantum Boltzmann machines, and one of the first things we did was we just looked at the problem of using the QBM ansatz for ground state minimization. So you just have, and let's just think of it more broadly. There's some observable, and you want to use a QBM ansatz to find the minimum or maximum eigenvalue. Nathan Wiebe, who spoke in the first session, he has a paper about this from some years ago where he has a proof under some assumptions. If you have a QBM with visible and hidden units, then you encounter a barren plateau. And for this problem, and I don't believe that his paper makes a statement about visible units. And so, you know, you're using analysis of like random Hamiltonians. And I'm curious if you have a sense of whether what you're doing here could apply to make some statement about that problem.
Yeah. So it's essentially a statement that in the glassy phase of these disordered systems, you shouldn't expect the mixing time of like a quantum Lombardian algorithm, like Jiaqing is going to talk about in a second. You shouldn't expect one of these algorithms to efficiently prepare the Gibbs state below this transition. So above the transition, you should expect Jiaqing's or others' papers and algorithms to quickly mix and therefore prepare these efficiently. So I imagine that I am not familiar with exactly the paper of Nathan's you're talking about, but I imagine that that's a setting where it's kind of below this transition. And there are also, I should say, systems where this transition doesn't exist. Like the SYK model is, I think, the canonical example of this, where maybe it exists at temperatures decaying with n, but at least at any constant temperature, as you're scaling n, this transition doesn't exist. And so you should expect to prepare at any constant temperature efficiently a Gibbs state, maybe not using variational methods, but using one of these Lombardian evolution algorithms.
Okay. I'll have more questions for
Okay,
you.
I'll be around at the discussion part too. So
That's
we
great.
can talk
Thanks a
about it.
lot.
Okay, so yeah, we will keep more discussions for the discussion session. Okay, so Jiaqing, yeah, good to see you. Yeah, long
Good to
time
see
no
you.
see. Yeah,
Can
okay.
you hear me?
Yes, I can hear you. Yeah,
Okay.
good.
So
So, Jiaqing, I will introduce you. Okay, so you can share your yeah, good. Okay, so Jiaqing obtained her PhD from Caltech this year, and she's currently postdoc at the Siemens Institute, and hosted by Umesh Vazarani. And yeah, I'm very glad to like collaborate with Jiaqing before. We previously had some nice collaborations on the T count and simulating HPTP maps. And Jiaqing has done lots of amazing works in quantum algorithm and quantum complexity. And today, very glad to have you talk here. Yeah, you can start. Yeah, hand it over to you. Yeah.
Okay. Thank you for the introduction. So like today I'm going to talk about the quantum algorithm for preparing Gibbs states. And it will be a quantum analog of the classical Metropolis algorithm. And the title is quantum Metropolis sampling via Iw-Qbm. So to begin with, I wish to first introduce like the key task in this talk. So the key task in this talk is called quantum Gibbs sampling, which is given a local Hamiltonian edge. So if you're from physics background, you might know local Hamiltonian is a math model to describe molecules. If you are from like computer science background or you are more familiar with machine learning, I would say local Hamiltonian is the energy function in the Boltzmann machine. So in quantum Gibbs sampling task, you are given such a local Hamiltonian or energy function, and you are given another scalar, which is called inverse temperature, which is supposed to be one of the temperature, but it's just a scalar. The task is you try to prepare the Gibbs states. So the Gibbs states is a mixed state, which is defined as the exponential minus beta h divides the normalization factor. So if you're looking at the spectral decomposition of h, this Gibbs state is just a distribution over n states. So that's the main task. So we were given a local Hamiltonian and we were given temperature beta, and we want to prepare Gibbs states. If you are from like classical, area, like you are doing, something about Boltzmann machine, this Gibbs states is in. So if you choose this H to be classical Hamiltonian, this Gibbs states, in fact, is exactly the distribution of the Boltzmann machine. So this is the key task in this talk. So before I proceed, in case you want to know a little bit more physics, you might ask, okay, where does this concept comes from? Like where does the Gibbs states come from? So from a physics perspective, Gibbs states describe molecules at a constant temperature. So for example, like if you want to study like a chemical reaction at relatively high temperature, or study the property of for example, like high temperatures for conductors, you might want to study the Gibbs states. So that's a physics background. But anyway, like in this talk, our main focus is given H, beta, and we want to prepare the Gibbs states. So before I go into any details, I wish to first convince you this is an interesting problem because there are many potential applications of Gibbs sampling. Since this is the Boltzmann machine workshop, the first thing I want to explain is that, in fact, Gibbs sampling is directly related to Boltzmann machine. So recall that Boltzmann machine, like either quantum or classical, is a model for model distribution, which is described by an energy function h. So Gibbs sampling is directly related to Boltzmann machine because Gibbs sampling is an algorithm which can help you to compute the gradient. So in the sense that so Gibbs sampling is an algorithm to prepare this distribution. Once you have this distribution, you just measure the state. So then you will get a gradient. So that's a connection to Boltzmann machine. But besides Boltzmann machine, like I also want to mention, like I think there are more like potential application of quantum Gibbs sampling. Here I just mentioned like two of them. So first, as I mentioned before, like one of the primary motivation for people to study quantum Gibbs sampling is try to solve problems in chemistry or physics. So this is because, as I mentioned before, like the concept of Gibbs states in fact comes from chemistry or physics, where this is a math model to describe molecules and materials at finite temperature. So if one day like someone or you have like very fast Gibbs sampling algorithm, you might be able to solve one of the most famous problem in quantum chemistry or condensed matter physics. And I think this might be one of the most application of quantum computers. And besides physics or chemistry, like I also believe quantum Gibbs sampling will, as Eric mentioned before, might have like potential to do optimization, because in classical world, simulated annealing are very successful, and simulated annealing is in fact a way of using classical Gibbs sampling algorithm. So that's a motivation. So like we have introduced a key problem of quantum Gibbs sampling, which is given H beta, prepare the Gibbs states. So now I'm going to talk about slightly more details, but before that, I wish to give a disclaimer. In this talk, we are going to give a rigorous algorithm, so I handle every details in a very careful way. So when we're talking about Gibbs sampling, in fact, we have two goals. One is called correctness, which means you want, so conceptually, you want to design a quantum Markov chain, which can converge to the Gibbs states in a finite time. So this is called correctness. But in practice, we definitely want efficient. We want it to be as fast as possible. So a disclaimer is in the following, I will mainly focus on this correctness part. So like, I'm going to give a quantum algorithm which probably converges to Gibbs states. And I won't prove efficiency, but the justification is I claim this algorithm is pretty simple, and I believe it plays a similar role as the classical Gibbs sampling, where many variants of this algorithm might be efficient in practice. So this is the goal. So like we have finished the introduction part, and then let's go to the technical part. So the key focus of the following talk is I'm going to explain my algorithm in details. Before that, I will first talk something about the classical Metropolis algorithm, and then I will talking about like our algorithm and the challenges. So let's first begin with classical Gibbs sampling. So like in classical Gibbs sampling, like for example, like you might just consider you have a classical Boltzmann machine, which is defined by energy function H. So in classical Boltzmann machine, like this energy function is defined on a graph. So for example, like a graph at here, where like on each vertex, you can choose a 0 or 1 value, and on each edge, there will be a penalty term. There will be a weight called Wij, which such that given like energy correspond to the two nodes of this edge. So it's a classical Boltzmann machine. So like in classical Gibbs sampling, the task is like given such energy function, we try to generate a distribution such that the probability of seeing a configuration is proportional to the Gibbs distribution, which is exponential over the energies. So this is the goal of classical Gibbs sampling. So you may ask, okay, like what's the most simplest thing people can do to generate this distribution? So there is a very fundamental algorithm which is designed like many years ago, which is called Metropolis algorithm, and this might be one of the most widely used algorithm for Gibbs sampling. So roughly speaking, it's a classical Metropolis is just algorithm which is a Markov chain, and which can converge to Gibbs distribution. And so like this is the overview. So to be more specific, let me talk slightly more on classical Gibbs sampling, classical Metropolis algorithm. So classical Metropolis algorithm is as I'm going to claim, I claim it's very simple and can be summarized by 2 sentences. So, okay, recall that our goal is to, prepare the distribution of classical of classical Boltzmann machine. So, in Metropolis algorithm, you only need to do 2 things in each iteration. So the first thing is you choose the random vertex and snip it. And the second thing is like you snip a random coin and choose to accept or reject. So what do I mean? So suppose we were working on a Boltzmann machine like this graph, and we want to prepare the Gibbs distribution. So the first thing we do is like we choose a random bit. For example, we choose this bit, and we propose to snip it. Like we propose to change the change this bit to be 1. But if we design our Markov chain just by doing this, like this Markov chain cannot convert to Gibbs distribution because this is too random. So the second thing we need to do is like snip a random coin, and with some probability you choose to accept, which means we set the next configuration to be snipping this bit, and with some probability we choose to reject, which means we reject this proposal and set the next state to be the original state. And this is the description of Metropolis algorithm. And the probability of this coin plays an essential role in this task. And so the probability of this coin should satisfy something called delta balance, which basically means like if you begin from Gibbs distribution, the portion of going out should equals to the portion of going in. But if you want to know like explicit formula, you can just write the probability of getting ahead as the minimum over 1 or the Iw-Qbm minus beta delta, where delta is the energy difference between 2 configurations. So this is all of the classical Metropolis sampling, which is pretty simple. So this is for the classical case. And recall that our goal is to do quantum Gibbs sampling. So, instead of considering a classical Boltzmann machine, you might consider quantum Boltzmann machine. Since the classical Metropolis algorithm is so simple, you might think, okay, why can't I just generalize this algorithm to quantum settings? Like, recall that classical Metropolis is, somehow it designed a Markov chain on computational basis. You might think, okay, in quantum case, we might be able just to mimic this process by design a Markov chain on eigenstates. So in this slide, I wish to convince you like there are some fundamental limits or fundamental challenges of doing this. So this is the reason is because it's hard to implement the reject case in quantum Gibbs sampling. Why? So a 1 sentence answer is because quantum state is unclonable. Which means like when you snip a random coin, if you get a reject case, you need to revert this intermediate state back to the original state, which basically says you need to revert a quantum state after measurement. And this is so in general, this is a very hard task and it's almost impossible. So that's why like there are some it's not that easy to design a quantum Metropolis algorithm. But today we're going to our ideas of handle this issue is by noticing 2 things. One is called weak measurement, which makes a reject case much easier to implement. And another one is called alternate accept. So I'm going to talk slightly more explain slightly more on our key ideas. And later I will give a more detailed description of our algorithm, which I personally think is pretty simple. So as mentioned before, our key idea to revert the measurement, revert to quantum state after measurement is by doing weak measurement and alternate accept. So what do I mean? So for weak measurement, we're changing the probability of this coin. So recall that in classical Gibbs sampling, like you snip a random coin. to decide accept or reject. So for weak movement, we basically just mean like we change this probability from something to something times a small number. So effectively, we are slowing down the chain in the sense that at each step of this random work, we only slightly change the state. And intuitively, this will makes it easier to to come back. And combine this with the quantum Zeno effect, you would be able to show like this helps the process a lot. So this is the first part. So basically, within weak measurement, you might believe it might be possible to implement this reject case. But something I want to emphasize and mention is like in the quantum case, even you are doing weak measurement, there are always some non-negligible probability that the rewinding process, like this process failed. So like there will always be something non-negligible. And in some previous work, they are just what they were doing, just keep trying back until success, which brings a huge overhead in the complexity. But what we notice is like in the weak measurement setting, instead of actively do anything, like trying to make this success, we passively just ignore this part in the sense that like we notice in the weak measurement setting, this branch in fact is close to the accept case. So instead of like actively doing anything, we just choose to accept this case and view this branch as part of the accept case. So this is the high level description. Now let me describe our algorithm in more details. I think our algorithm is at least conceptually pretty simple, which I'm able to explain in very details in a short talk. So as I claimed before, our algorithm is very similar to the classical Metropolis. With some accept or reject case. So similar to what I said for the classical gift sampling. So for the classical Metropolis algorithm, I say like the step we are doing is first find a random node and snip it, and then snip a random coin. So our quantum Metropolis algorithm is similar in the sense that we first do something random, and then snip a random coin, and choose to accept or reject with some probability. So more precisely, one iteration of our algorithm can be described by this graph, which I'm going to explain step by step. So before that, obviously, this graph should be interpreted as one iteration in your Markov chain. And our algorithm, or just consider the classical Markov chain random work, is like you perform the same step again and again. So that's that's how you use this algorithm. Anyway, this graph represents one iteration of our algorithm. In this algorithm, suppose at time step t or time step n, we were have some initial state phi, some unknown initial state phi, and in our algorithm, we will use 3 more registers as Ansela qubits to help the computation. So as I said before, the first thing is do something random to disturb this phi and go to some other random place. This is done by this unitary U, which is as follows. What does this U do? So this U first perform a phase estimation on the register 1 and 2, and store the energy of the current state to the second register. And then you just do something random, you can apply an arbitrary unitary. For example, you can randomly choose a single poly and apply the single poly. And after that, you perform another QPE, which estimate the energy after the proposal to the third register. So the reason we were doing 2 QPE or something like QPE is because in Metropolis algorithm, the probability of the coin depends on the energy difference. So this is something you need to store before you flip a coin. But anyway, like in the first step, you just do something random. And similar to classical Metropolis algorithm, the second step is like, you try to flip a random coin. So the first thing you do is to compute the probability of the coin flipping, which depends on the two energy difference. So in quantum, you can just encode this classical computation in a controlled unit array, which is this W. So W is just a control rotation, which takes 3 inputs. So the first 2 inputs is the energy on the third, in the third, second, and third register. So basically W is like controlled condition on the 2 energies, and you compute a controlled rotation. You rotate the last qubit according to the probability. So here FEE prime is the probability of this coin, which is the minimum over 1 and exp minus beta delta. So W is just a control rotation, which computes this probability in superposition. And here, one thing I want to emphasize is like, as I said before, like weak measurement is a key thing in our method. So here weak measurement is nothing more fancy than just changing this probability. So basically, weak measurement means like we change this probability from F to F times the small number. So that's all we mean for weak measurement. So this is the W. So similar to the classical Gibbs sampling, like when after you flip a random coin, you try to observe something. So that's why like we apply W, then we perform measurement. So we measure the last qubit. So if we get 1, this will hit one more. So in case you want to know the full version of W, it's just a controlled rotation, and the W is a unitary. So after we apply W, like we want to we are going to like measure the last qubit. If you get 1, you will this correspond to an accept case. And here accept is just a name, and all the thing we are doing in this black box, which basically just tracing out all the ancillary qubits and refresh them with 0 and go to the next iteration. So that's all we do. And if we get 0, so if we, after this measurement, if we get this part, if we get 0, this will correspond to a reject case in the classical Gibbs sampling. So in the reject case, what we were trying to do, or intuitively what we should try to do, is try to reverse the process back to the state, original state. And the most natural way of reverting back is just performing the inverse of the operation. So previously we perform U, W, and measurement. So the most natural way of reverting back is apply W dagger and measure and apply U dagger. So that's what we were doing here. So so when you apply W dagger and measure, you again have 2 possibilities. So if you get 1, this will correspond to an alternate accept case, where again alternate accept is just a name, and what we were doing is this black box, which is tracing out, throw away all the ancillary register and refresh them with 0, and go to the next iteration. So here we give it a name as alternate accept because in this case, although it belongs to this big reject branch, but in this case, in fact, the resulting state is not close to the initial state. It's in fact close to this accept case. So that's why we give it a name as alternate accept. And if we get 0, then we will keep rewinding. Like we keep replying this U again. And this will correspond to a reject case in the sense that the resulting state will have similar energy as the initial state. But again, like no matter, all those accept, alternate accept, and reject are just names. And the operation we're doing is again this black box, which is throw away all the ancillary register, replace them with 0, and go to the next iteration. So that's this is the detailed description of our algorithm, and our algorithm is just doing this again, and again. And one more like information I want to give is like in our algorithm, in fact, we record energy information along the way. So if you want to compute some energy function, like you can just use this information. You don't need to do anything more. So that's the details of our algorithm. So you may ask me, how does this compare to existing work? So a short answer is like, I think our work is very simple. Just recall to make a comparison before with previous work. I mean, just first recall like the key technical challenging of designing a quantum Metropolis algorithm. I mean, it's reverting a state after measurement. So there are two work which is highly related to our work. One is using Metropolis rewinding, which is using a very long sequence of rewinding instead of in our case are only like accept alternate accept. The key issue in this is like the error, the proof is not correct. So that's a key issue. And another only until very recently, like people designed the first proven correct results based on something different called depth generator. So this is proven correct, but it differs from Metropolis algorithm in the sense that it has a lot of advantage. It has a very good math property, but just conceptually it's a little bit complicated, and there's a gap between understanding this and understanding what's happening in classical deep sampling. And our work, the motivation of our work is just try to do something simple, and we did success by doing weak measurement and alternate accept. And our main motivation, or something I want to convince you, is like our algorithm is simple and very close, conceptually very close to the classical Metropolis algorithm. And we hope like this will help it much easier to generalize classical techniques to quantum deep sampling. So when I say techniques, I mean both rigorous and heuristic techniques. In classical deep sampling, like Metropolis algorithm is a fundamental algorithm, but it's just the beginning of the story. And there are so many variants of deep sampling algorithm based on Metropolis, which can work much faster in practice. And we hope our quantum Metropolis algorithm make it easier to generalize those kinds of ideas to quantum case. So besides, I also want to just mention. So this year there are a lot of works on this topic, and there are some like algorithm which are based on system-based interaction, which is more in some sense like it's more like good for like physical interactions, for implementing on like analog quantum computers. So yeah, I almost run out of time, but I'm also almost finishing. So in summary, like what I'm saying is, we design a like quantum Metropolis algorithm, which can convert to deep states, but the efficiency part, is widely open, and I think they only this year or last year, like there are some work on this direction. So also as like Eric mentioned before, like you may ask, the key problem you may ask now is like when this will be efficient. So the thing we know, so like this year people, there are many factors determine like whether this algorithm is efficient or not. So one is the temperature, and one is the dimension of the lattice. So it's the structure of your like energy function. So for 1D case, you can prove they can, this is all the algorithm, especially the depth generator one, is efficient. And for high temperature, you can also prove you can sample in point n time. So the real hard part is like when there are some low temperature and when there are some like ordered phase. So that's the hard part. And need to be widely explored. And also like I'm also very curious about like what's the right structure for Boltzmann machine, and it will be interesting to explore whether like those kind of deep sampling algorithm is efficient in the interesting structure in Boltzmann machine. And finally, like I also want to slightly mention some, and this is the final page. So one thing I want to mention is like, we were doing GIF sampling, but I want to mention maybe like just directly computing the observer value by some way is much easier. Because I mean, GIF sampling is too hard. So I'm thinking about this for a while, but not succeed. But like we can still get some results. So like the intuitive thing is like we try to, I mean, I think it's the interesting thing to thinking about whether estimating observer value is much easier than just preparing GIF states. And we were able to show like in many cases you can get effective independent sample using a time much smaller than the mixing time. So in case you are interested and also attend the Iw-Qbm workshop, I will give this talk. I will present work on this workshop. But okay, this is the final one. Sorry. Yeah. So that's all. Like, thanks.
Very nice
I guess
talk.
don't have time for.
Yeah,
question.
we have
Yeah.
let us have a quick question. Any questions for Jiaqing? Yeah.
I have some questions. This is Mark Wilde. Thanks a lot for your talk and for accepting our invitation to speak. I actually have a number of questions, and so maybe I'll just ask a few and reserve more for later.
Yeah.
So it was great to have the very simple description of the algorithm. That's really nice. You talked about picking C, and you said you described it as doing something random. And then you said, for
Yes.
example, a single qubit Pauli. Does that suffice, or what do you need to get your proof to work?
So for the proof to work, you can choose arbitrary.
Arbitrary what? Sorry.
Like okay, so condition if you can choose this to be an arbitrary random unitary. I guess you are asking if you want unique fixed point. The thing you need is like the set of operator you are choosing forms a full algebra. So for example, all the single qubit poly when they form the algebra, they can form the full algebra of the Hilbert space. So that is sufficient.
I see. That's really nice. It's nice and simple. What was FE prime in your algorithm? Was that just the difference between the energy E and E prime?
So it's a minimum over 1 and the EXP minus beta energy difference.
Oh, that
so in
was
the
from
Metropolis rate.
the classical algorithm. Okay.
Yeah.
That's nice. I'll just ask one more quick question. In many applications, it's very useful to have the purification of the Gibbs state. Does your algorithm do that also?
No. So like I think like I think our answer would be like you can do some. I think all the existing purification. Okay, so like I'm talking about in the Nimbladian picture. I think it needs a guided states.
Okay.
Yeah, because you transform some. Sorry.
Go ahead. Sorry.
Yeah, like you transform a Nimbladian into a gapped Hamiltonian, but preparing the ground state of gapped Hamiltonian is not an easy task without a guided state.
Mm-hmm. I thought
sorry,
these algorithms. I thought in these algorithms for making purifications, typically they just do something on one share of the maximally entangled state, and then that often works to get a purification of the Gibbs state. Can you not do that here? Like, is there a way you can just run your algorithm coherently and then you would get the purification?
Okay, like maybe like I haven't think about this very carefully. This is the first time I'm thinking about this.
Okay.
But I still think I think there's one case you can probably prove you can prepare the given states is when you have like simulated annealing path from something you already know, then you can prepare the purified given states. I think like equivalent, you can also ask the same question for classical given sampling, right? Like suppose I have a classical Markov chain, which can prepare a Gibbs distribution. Like can I use quantum computer to prepare the purified state? People call it Q sample, and once you have Q sample, you can reduce dependence on the, epsilon from something from 1 over epsilon squared to 1 over epsilon. So that's a huge increase. But as far as I know, we are not able to do this in general. Like we are not able to do this for general Hamiltonian. Only some special case.
Okay, thank you.
Okay, good. Very nice discussions, and let us leave more for the discussion session. Okay, good. Next, we will move on. Our next speaker is Lei Zhang from HKUST Guangzhou. He is currently a PhD student and with research interest on quantum algorithm and quantum software. Lei, could you share your screen?
Yes. Can you see my screen?
Yes, good. So, yeah, it's your stage. Okay.
Okay. So today I'm talking about quantum imaginary time evolution, how to efficiently simulate quantum imaginary time evolution. So in previous talks, I think some speaker has already involved imaginary time evolution, either implicitly or explicitly. So in this talk, I will talk about how to prepare the imaginary time evolved states with polynomial resource with adequate assumptions. And this is a collaboration with Professor Xing Wang. And hold on a second. Oh, okay. Yes. I'm sorry. And here is a problem of imaginary time evolution. So for Hamiltonian H, we are required to given an initial state, and we need to prepare the normalized solution of imaginary time Schrödinger equation. The difference between imaginary time Schrödinger equation and real-time Schrödinger equation is just a difference of a constant I. And here tau, we use tau to denote the imaginary evolution time, and we call the operator that maps Cat5 the initial state to the imaginary evolution time at time tau. We call that the imaginary time evolution operator, also called the ITE operator. And the application of imaginary time evolution, firstly, it was mainly used for ground state preparation and also for given state preparation. And later, people found out it can be also used for open system simulation, so that for example, the Lindbladian, it can be decomposed into the real-time into a product of real-time evolution and imaginary time evolution. Just make n goes to infinity. And people also discover other applications, such as computing the n times correlation functions of Hamiltonian recently. Also, Professor Dong Deng also shared how to use imaginary time evolution in data classifications. And there are also some old discussion on how the analysis of imaginary time evolution on quantum mechanics, quantum field theory, etc. So let's move on to existing work on how to do imaginary time evolution. So there are two routines for imaginary time evolution using quantum circuits. So the first routine is just we fix an initial state. We make the initial state as given, right? So we find a physical unitary that maps this state to the imaginary time evolution and time tau. So under this routine, there are three schemes. First is a PQC scheme, just to use variation ansatz to find the a group of parameters that the optimized parameters can match such unitary. And second one is similar to the PQC scheme. I mean the circuit scheme. The manifold scheme is just you also use optimization programs to find such optimized unitary, but it is based on optimization of a manifold, so that it contains some theoretical guarantee. It's just a partial because it still requires measurement precision, and etc. And third one is the main one is the using Schroeder scheme. You just use a product of a large amount of real-time evolutions to approach this unitary. And this TJ and AJ are just computed using the by measuring the circuits repetitively. So the advantage is that this scheme, nearly all algorithm can prove either numerically or theoretically prove that it can achieve a polynomial resource complexity in system size, and it can execute without failure. Because I mean execute without failure, you just follow their algorithm and you can get their desired result. The advantage is that because the initial state is fixed, when you change the initial state, you have to do the entire algorithm again. That the information cannot be reused. And the another downside is that we are not sure that how this algorithm perform when the imaginary time evolution time just prolongs. The error and the resource costs may increase exponentially as the evolution time increases. And that's the routine one. Routine two is just it's simple. It's just for unknown initial states. What they do is that it use a quantum circuit to directly simulate the IT operator. But since the IT operator is non-unitary, I mean it's not even physical, so that such simulation will lead to failure. Such failure may be indicated by the, for example, by post-selection. If we fail to do the post-selection, then that indicates failure. The advantage of this routine is that it also achieves polynomial resource complexity in system size, and it is theoretically analyzed so that it works for any initial state. But the downside is very clear. Although it has theoretical guarantee, its success probability can decrease exponentially as the imaginary time increases. And I call it the exponential decay problem. So that in short, the existing work for long time imaginary time evolution. So these algorithms are either heuristic, that is based on some variation measures, or they are theoretically infeasible. So in this work, we present that's something that is theoretically feasible. To start with, we talk about some wait a second. Can you hear me?
Yes.
Because I see in the conversation that some people does not have sound. Okay.
We can hear you. You can continue.
Okay.
It dropped off for like a second, but now it's fine.
Okay. Oh, okay. So now for the we start with the transformation of quantum data. So that's this unitary. It can apply rotations. So all unitaries are rotation with respect to this eigenspaces. So for example, the eigenfaces is just the angle of this rotation, and the basis of this rotation is the eigenbasis of this unitary. So if we want to apply a transformation in F, then such transformation will directly reflected as the eigenvalue or the amplitude of such of the rotation, but the eigenbasis remains unchanged. And only mainstream quantum algorithm can be considered as such eigeninformation procession. For example, when we try to extract the target eigenfaces, we use Shor, HHL, and quantum amplitude estimation. And if we want to amplify the target eigenface, we can do quantum Hamiltonian simulation and Grover's algorithm. They all correspond to different function f. So for imaginary time evolution, we also use such a function transformation. We use a quantum phase processing. It's just a multi-qubit a quantum signal processing based structure to simulate such transformation. This circuit is composed of two lines. The first line is just an ancilla qubit, and it's composed of RZ rotations and RY rotation. And second line is a unitary. Encoded by some data, and together they can simulate the transformation of the unitary. And such P and Q are polynomial transformation. Oh, I'm sorry, the trigonometric polynomial transformations, and P and Q are Fourier polynomials, whatever you like to say. They are Fourier polynomials on basis of e to the power of negative I over 2 and x over 2. And the P and Q need to satisfy the same degree and same parity. So let's start again. All right. To use this process, we can use to simulate the exponential function by computing the Fourier approximation to the exponential function. We first, the left bottom side gives the approximate procedure. We can compute the Fourier approximation of the exponential function, and we then compute the rotation angles for the ancilla qubits, and we construct the circuits, and we do the post-selection. And but this problem, this cause some problems because if we naively choose the function to be the normalized exponential function, then its success probability will decay. Like previous work also used QSP-based algorithm to do so, but they failed to solve this exponential decay problem. So that a naive choice will raise this problem. The second idea is a cool idea, is that we, instead of considering the normalization exponential transformation with just a naive normalization, we consider an adaptive normalization factor, such that the overall function can be adequately approximated with a good success probability. And here comes our lemma 1. We show that as long as the normalization factor the blue one over here can be within the ground state and within the ground state energy, so that we can output and approximate imaginary time evolved states with success probability that can lower bounded by a constant. When I mean constant, I mean a quantity that is independent of the evolution time, so that the overall success probability is lower bounded by something that is not dependent on the time, so that we avoid the exponential decay problem. And here is the numerical demonstration on how this performs. By assuming that we make some assumptions without loss of generality. We assume that H is normalized with the negative ground state energy. We also assume there are long imaginary time evolution. And we assume that the overlap between the input state and the ground state is non-zero. And for the last assumption, if the overlap is 0, then we may consider the overlap between input state and the first excited state, which does not affect the final result of imaginary time evolution. As shown in the right graph, it shows that if we can identify such lambda in the, I call it comfort region, then the success probability is lower bounded by the red line, and with sufficiently good state infidelity with respect to the imaginary time evolved states, and which then solve this problem. And we later consider the assumption that that we are no longer given the evolution oracle of the Hamiltonian. In that case, we will consider Chota decomposition of the evolution oracle. And then in that case, we may need to make some assumption that are specific to this problem. For example, the overlap need to be cannot decay exponentially as the system size increases, and the Hamiltonian need to be non-degenerate. Such gap need to be satisfied that the imaginary time evolution is long enough such that the gap can be distinguished. Mathematically means the e to the power of tau delta is at least polynomially large with respect to tau. So under these specific assumptions, we show that we can approximate the target state to polynomially small errors in inverse imaginary time using polynomially many elementary quantum gates with a single qubit. So that means that unlike previous work, here I show some previous work where heuristic algorithms are not listed in this table. So manifold-based case, although it has theoretical analysis, but steps decays exponentially. Other theoretical works, they are either they have circuit depths as well as other hours, but their circuit runs may decay exponentially. And our results show that the overall resource cost can be controlled in a polynomial sense, so that we proves that the imaginary time evolution can be prepared in polynomial sense resource in terms of evolution time. Because if we assume that the ground state overlap is reasonable, then we can also claim that it can be prepared in system size. And as an application, sorry, here is a summary just for this part. If we use a ground state energy estimation of precision that is linear with tau, then we can use it to prepare the imaginary time evolved state of precision that is polynomially related to tau, so that it is kind of worthy to use energy estimation algorithm to do so. And in a more abstract sense, why the exponential IT states as a result of exponential transformation can be prepared in polynomial sense, because multi-qubit based QSP circuits, they are independent of system size. So, and second one is that the exponential transformation can be approximated with Fourier polynomials in a super polynomial convergence, not exponential. Super polynomial convergence, when I mean super polynomial convergence, it means if the precision is epsilon, then the degree of polynomial, that is the degree of circuit depth, is about polylog epsilon, and that degree, not epsilon, not log epsilon. Yes, and we rely on assumption on reasonable ground state overlap. Otherwise, our algorithm cannot be scalable in system size. That means our algorithm, cannot be directly applied to give state preparation. Because we are simulating the IT operator, not directly to the give state. As an application, we show that how our algorithm can be used to do ground state preparation and energy estimation. This is a common topic. It just asks you to given a non-degenerate Hamiltonian to find this ground state energy and to prepare its ground state. And the common query model is the same. It's just an evolution oracle of the unitary. And why imaginary time evolution can be applied to ground state problems is because the imaginary time evolved states can converge to ground state as tau goes to infinity, as the imaginary time goes to infinity. And such rate of convergence is at if the delta is large enough. So if that's tau is large enough and delta is large enough, whatever. But in that case, we can use a ground state energy estimation of that is linearly with respect to tau to get a polynomial precision, and then use that to prepare ground state. I know it kind of sounds strange to use a ground state algorithm to solve to make a new ground state algorithm, but it is worth it to do so if we interruptedly use in using imaginary time evolution in an intermediate step to obtain a better precision. So the only problem is how to find such tau, because we have no information on delta. So we don't know how to find such tau to be large enough. We don't know how large we should choose to appropriately solve this problem. So the problem we are solving is that we are not only finding the ground state energy, and to prepare the ground state, we need to find the such tau first, such evolution time first, so that we can use that to prepare the IT state. But since IT state can be approximately equals to ground state, then the ground state problems get solved. The spirits, because I'm running out of my time, because I will quickly go through this. The spirits is that we are using taking the expectation value of circuit, I mean the QPP circuit or the QSP-based circuits that prepares the IT state with respect to the Hamiltonian. And we find that this quantity can decays exponentially until it meets the ground state energy. That means we can repetitively guessing the normalization factor and observe its rate of change to detect whether the guessed normalization factor converge to the ground state energy. At the meantime, we gradually increase the time of tau, the guess of tau. Sorry, so that's that is our algorithm sketch. We repetitively measure these circuits that prepares the imaginary time involved state. At the meantime, we will shrink the guess of time, and we get the estimation of ground state energy. When the search interval is small enough, and this estimation of ground state energy converges, we return all these quantities at once. So that in the end, it goes to this following theorem. That means we only need to, for a precision that is B precision of B gamma -1 and tau -1. B here is just some quantity, and we can use circuit depths. We can use algorithm with circuit depths of tau. We only linearly with tau to obtain this estimation. But as a trade-off, we use many measurement shots because we are taking the expectation value. So by halving its inequality, it is just the standard quantum limit instead of the Heisenberg limit that usual ground state estimation algorithm gives. The result we compare with existing work, and that we can achieve a query depth. We can reduce the query depth by a factor of gamma -1. Gamma is the overlap between initial state and ground state, which is usual in these methods. And the summary is that we can obtain a shorter circuit depth, but the trade-off of more queries to the UH. UH means is the evolution oracle of the H. And later we take experiment about anti-ferromagnetic Heisenberg models. We show that we can simulate the imaginary time evolution up to tau equals to 50. And please note that in previous work, this scale can only scale, a numerical experiment can only scale up to 20 or something. And we show that this imaginary time evolution can be adequately simulated, and it can be used to solve ground state problems exponentially as the guess time increases, as you can see from the graph. In particular, in part C, we show that as the resource cost increases, the error will decay exponentially. But as tau satisfies, such error decrease will reduce to the standard quantum limit, as I discussed before, and then it will fluctuate and reduce to the square root decay. I mean, the error will decay in a square root as the resource cost increase. So as a summary, we discuss IT algorithm that can have polynomial resource dependence on evolution time, and we apply it to ground state problems that can reduce circuit depth. Potential caveats, there are many. I mean, the main concern is that we did not consider the classical machine error during the theoretical proof. which is actually essential in numerical experiments. In that case, the Fourier convergence will no longer be super polynomial, but polynomial convergence. That means it may cause problems in real implementations. And that is the end of my presentation, and I'm waiting for questions if possible.
Okay, thanks for the talk. And any questions for Lei?
I have a question.
Okay.
So when you do numerics, are you doing it for 1D or 2D?
You mean the model is 1D or 2D?
Yeah, because I think they have some so I feel 2D is totally different, a totally different story from 1D.
Okay, we are doing in I think I'm doing in 1D. It's a linear homogeneous chain. So
Okay. Okay.
but I still think this is maybe a strong correlating model, so it may have physical meaning.
Yeah.
The behavior may behave differently if this energy spectrum are different. So if this model has degenerate energies on ground state subspace, then the algorithm will get better. So that's because in that case, the required imaginary time for the evoked state to be the ground state will be shorter.
Okay, thanks.
Good. Any more questions for Lei? Okay, so if not, we will continue to the discuss session, and we'll go to talk with the speakers just the same order of today. And for first speaker, Tongyang has some issues need to handle, and if you have questions for Tongyang, just feel free to just drop him an email. He will reply. Yeah, that's what I know. Okay, and then is any more our second speaker today is Eric. So any more questions for Eric? I think Mark, you said you have like reserved questions for him, right?
Yeah. I'm trying to think of more discussion items.
Sure.
I think I would need to read your works more carefully, but the message I gathered is that you're able to make like average case hardness statements for various quantum algorithms, which include like thermal state preparation algorithms, right?
Yeah, exactly.
And there was also this commutation index, is that what you called it?
Yeah, so in a paper from before the ones that I talked about today, we showed that if this commutation index, which it's shown up in other contexts too, we're not the first to look at this. If this vanishes asymptotically as you grow your system size, this is essentially a measure of there being lots of frustration in your system induced by uncertainty. So one example of this is if you have, a completely commuting model. So you just have Z polys here. This commutation index achieves its maximal values. And then if you consider, for instance, like two local sum over all poly operators, all to all connected or something, it's some absolute constant. I think it's like 1/9. And as you increase the locality of these operators, so you do like n to infinity, then locality to infinity after that, this measure also decays. And essentially, if you combine all of these results I've collaborated on, what you see is that if this measure is like greater than some, what's the best way to put it? You can show that if this quantity is too small, then you have this glassy kind of behavior. But if it's, if it's too large, you have this glassy behavior. And then if it decays quickly enough, then you can show that your system doesn't have this glassy phase transition at a constant temperature. Yeah. So it's kind of a weird situation where you kind of expect that as you have more of this strange frustration induced by quantum effects, the problem actually becomes easier. And the way I think about this is actually not that the problem is necessarily becoming easier, but the bar you have to achieve to get to a low energy state is much lower. So in other words, like because of this frustration, that brings up what, in a rough sense, what the maximal or what the ground state energy is. So like for fully commuting, you have less of this frustration. So the ground state's much lower than if you had kept that normalization and then added these non-commuting terms. And so you actually are achieving a better and better fraction by achieving the same energy as you would otherwise. But so it's kind of a counterintuitive situation where the more of this frustration you add from this quantum source, the easier in terms of approximation ratio it gets quantumly. And that's also true for sampling. So for Gibbs state preparation, there's some temperature where below this temperature, you hit this spin glass phase transition, and you're going to have long mixing times and everything. And so what I'm interested in now is above this transition. So at beta minus epsilon, I'm wondering if there's a way to show that you can efficiently, using a quantum computer, reach this temperature. Because then it would show that this is like exactly tight, which is effectively what's known classically up to some absolute constants. Anyways, so classically, this seems to be the right way of thinking about these average case hardness of sampling. And so it'd be nice to have a similar picture in the quantum setting.
Okay. I have another follow-up question, which is just sort of another kind of take-home thing for me. For let's suppose you have like a random Hamiltonian model, and you want to talk about average case hardness of preparing a Gibbs state. Do you have some function that we can just plug into and evaluate, and it'll give us like a lower bound on the time needed to prepare the state?
Unfortunately, it's not that simple, but at
Okay.
least for the quantum easiness, it's fairly doable. So here I showed that, okay, there exists a temperature, if it's sufficiently, there exists a sufficiently low temperature for many of these disordered models where you have the structure and you can't prepare a Gibbs state below that temperature efficiently. And at least in the models I looked at in my paper, you had to do some very mathy things to prove this. Like it's a lot of work. And then in the second paper with collaborators, it turns out you can use physics techniques to make it easier and prove it in more settings, but it's still pretty hard. But for the quantum easiness aspect, so to show that when this commutation index, or rather to show that this commutation index implies quantum easiness at some temperature, or shows it's not glassy at some temperature, and presumably it means fast mixing. You have to measure this commutation index, and to do that is you can bound it using an SDP. So if you show that this the solution to this SDP scales in a favorable way, then that suggests you have fast mixing at a temperature given by like the inverse of the solution to this SDP. So they're at a beta that is like this.
What is
So
that SDP? Was that in your slides, or I don't remember
so
that
it's
in the
in
slide.
wait,
You can also do a
paper.
screen share if you have something.
Yeah, sometimes Zoom breaks if I do 2 screen shares in a row. So let's see if this works. Okay, it's not working. But wait, oh great, I think Zoom.
Oh, we lost Eric.
What?
Oh, we
Yeah.
can now admit him from the waiting room. Okay.
Okay, as I predicted, Zoom crashed. But let me get you the link, the paper that shows this.
So you were fine sharing your slides, but then somehow
This is the weirdest bug that if anyone has a solution, please tell me. I'm on Linux, but if I share twice my screen twice in a meeting, it crashes. The first time it's fine, and then if I share it a second time, it crashes Zoom. But this is the paper.
Do you have the PDF form?
Okay.
Say that again?
I've never had that problem with Zoom.
I know it's only happened semi-recently, so I haven't had time to debug it. But yeah, it's a very bizarre issue.
I think you can share your PDF form, and it's more stable than the PowerPoint. Probably.
Oh no, this was PDF. This is just generally, it's a Wayland issue, I think. Anyways, yeah, it's definitely a computer issue and not a Zoom issue. But I can try again now that it crashed once. Maybe that resets the counter. Let's see.
I mean,
Good luck.
Oh yeah. Oh no, it still didn't work.
I can do a screen share. So this is your paper. Where's the SDP? Is it this?
I think he's gone.
Oh, okay.
But he might come back, I guess. I guess his room crashed.
Yeah. Are you there, Eric?
I'm back now. Yeah, sorry.
So I have your paper on screen share.
Right. So if you wait, let me pull it up too. So if you look at theorem 2, scroll down, it's on page 2. Yeah.
Oh, on page 2. Okay.
Right. So this is a statement about concentration of the partition function, which doesn't necessarily mean anything, but physicists believe that if these two quantities, sometimes they're called the quenched and annealed free energies. You might hear
I've seen that, yeah.
term thrown around. If they're equal, that implies you don't have this glass phase transition at that temperature. And it's kind of more subtle if the inverse is true. Like often if they're not equal, you actually have a spin glass phase transition, but there are some counter examples to that. But at least in this direction, it's pretty like widely believed that if these two things are equal, then you are ergodic at that temperature. And so, okay, here we report it for the SYK model. Wait a second. Do I have? Okay, it might be in the supplemental where we give the generic statement. Oh no, it's sorry, theorem 6. So equation 12, there. Right. So this delta, this commutation index, essentially controls how close these two things are, these two quantities. And so if delta is asymptotically vanishing in the thermodynamic limit, then that says that for any constant beta, these two quantities are equal.
Oh, that's nice.
Yeah. And so if you believe physics things, physics heuristics that essentially says that you would expect things like Jiaqing's algorithm to have fast mixing.
Okay.
And roughly because this delta is measuring how anti-commuting, or rather, the larger it is, the more commuting the terms in your Hamiltonian are. So it essentially says that the more anti-commutation you have, the better, the more closely these two things match up. And you can upper bound delta using an STP, which say, okay, it's it's in the discussion section because it's a letter, but in the supplemental information, we also talk about it. Essentially, other people have shown this commutation index. If your Hamiltonian is like a sum of Pauli operators with disorder, like IID Gaussian coefficients, it depends only on what's called the commutation graph of your operators. In other words, if I drew a graph where every vertex corresponded to an operator in the sum, and then I drew an edge every time that pair of those pair of operators anti-commute. It's like it's anti-commutation graph.
All right.
It's some graph property, this commutation index. And this graph property is upper bounded by the Lovász theta function, which you can compute efficiently given a graph. So that's how it all links to an STP in the end.
Interesting.
And you can lower bound it using the like independence number or something. I forget exactly, but that's inefficient. The upper bound is efficient though.
Okay. I see. Very interesting. Looks like a good paper to read. Yeah, we were a few months ago reading a lot of these kinds of works. We were thinking about the barren plateau problem for QBMs and thinking along these lines that you're doing here, that you pick these for a QBM, these are like the parameters, right?
Yeah, exactly. Yep.
And you pick them at random, although for QBMs, I don't know if we would do this normalization. That's probably essential for your proof.
Yeah, so this normalization often makes sense in these disordered models because they're so frustrated that your energy isn't scaling, with the number of terms, it's scaling with the square root of the number of terms. But nothing breaks because none of this is asymptotic. Equation 12 is just exact. So if you rescale everything by m to the 1/2, it goes through.
So if we were to remove this, would an m pop up over here or something like that? Or do you have any?
Yeah, exactly. Yeah.
So that would scale delta?
Yeah, delta is also written in a way that depends on m, though.
Okay.
Or depends on this normalization. So the factors cancel there. But
okay. And this same bounds what you would have.
Yes, I believe so. I mean, it should, if you're renormalizing beta and you're renormalizing h, the result shouldn't change, right? So like
good point. Yeah.
So however you normalize it, as long as you do it in a consistent way, it should be fine.
That's good. Thank you. Cool.
Okay, good. Any more questions for Eric?
Hi, Eric.
Hey.
I may put a small question. Thanks for your nice talk, firstly. I got a forward question for you. Like, the concept of quantum OGP, is that correct? Right? Is it can this formulation provide some new insight for general quantum machine learning model design? Because I'm just realizing that it's kind of like
right. So actually, one implication, for instance, is that if you tried to use like a variational quantum algorithm, which some people call quantum neural networks, if you tried to use one of these at low depth to find the ground state of a Hamiltonian that has this property, it would fail. So this is similar. You might be familiar with these results that say QAOA at log depth fails to optimize like max XOR sat or something, like these combinatorial optimization problems that have the classical version of this property. This result essentially is the quantum generalization of this, both for the, well, not only is it a quantum generalization of the problems you can apply it to, but also it generalizes the algorithms you can consider. It says any algorithm that has this stability property fails for any quantum system or classical system that has this topological property. So that includes things like shallow quantum neural networks.
Oh, makes sense. Thanks a lot.
Okay, good. So good. If you have a question, just feel free to raise hand
shoot me
or
an email.
text. Or email. Sure. Okay, and okay, we just continue. And next speaker is Jiaqing. Any more questions for Jiaqing?
I have some.
Yeah.
Yeah. Could you give us, so I mean, you gave us a sense of the algorithm, and then I think a lot of people are aware that these errors popped up in the proof of David Poulin et al. Can you give a sense, I think you did a little bit, but what is it about, or can you give us a sense of your proof, why there are not errors? And what you did to fix the problem, and if you could give a sense of like why it works, because like I think from your talk I could follow the algorithm. It was so nice and simple that that's there, but I didn't have a sense of that aspect.
Yeah. Okay. So to your first question, like why? So you were So the old paper. First, although the proof is incorrect, but I would say I'm not sure the argument is incorrect. So when people say there are errors in that paper, the proof is incorrect in the sense that to make the proofs works, they assume like there is a special version of quantum phase estimation, which is first is boosted. Basically means like this phase estimation is sharp, the tail is small, and then besides they assume this QPE is shifting invariant, which basically means like this QPE. So when we use quantum phase estimation, when we use QPE, typically we initialize the ancillary qubits to be 0, and since they are using Merge-Rogers rewinding, like they will reuse the same ancillary qubits for poly n times. So they need the algorithm to be well behaved when the ancillary qubits is not 0, in the middle of the computation. So that's why they say shift invariant. And when people say this, this proof is not correct because people can prove there's no such kind of QPE does not exist. So that's why the proof is incorrect, because the assumption is incorrect. Like that's impossible. And why our algorithm? So to answer why our algorithm works. So first, when we are not doing Merge-Rogers rewinding. So Merge-Rogers rewinding is in a reject case, you try to come back to the initial state. You keep doing for multiple times, for n times until success. So we are not doing Merge-Rogers rewinding, so we don't need shift invariance. It's because we only run rather running for like 2 times. I think that's a reason. That's the first reason why we don't run into the same issue as them. And a more like intuitive reason why our algorithm can work is in fact from the Lando effects. So as I said before, like so why weak measurement helps? Because just imagine, so when we say like one cannot revert a state after measurement, this is a weak statement. So the precise statement is like you can revert the state by some errors. And by quantum Zeno effect, the errors is of a higher order than the correct part. So when you make the step to be small, like the accumulated error is small.
Mhm. I see.
Yeah.
Okay. I didn't have a sense of the efficiency of the algorithm. So you said like you kind of made statements like I think poly n, but I didn't have a sense like given a Hamiltonian and a temperature, is there some formula we can plug into to understand like the runtime of the algorithm?
So first for the algorithm, like I only prove correctness. Like I even didn't show it converts in point n time. And in general, like I think that will be QMA hard for general case. And if you so to find the formula, I think that I think so far like there's no formula, but there are some intuitions when it will work or will not. So for example, imagine classical Hamiltonian. There are already a lot of existing literature, and people can get intuition from them. And roughly speaking, like I think for 1D Hamiltonian, for 1D quantum Hamiltonian, like people can prove at any constant temperature, it can convert this in point n time. Let me make sure, like, so are you satisfied with point n time, or you're asking for something more efficient?
That seems fine. Yeah.
Yeah. So like for 1D system, like in physics, people know it don't have the like constant temperature phase transition. So I would say like the intuitive thing when it works, the intuitive answer is when the Gibbs distribution is somehow close to a product distribution. It's not really close to product, but for example, decay or correlation. Strong decay or correlation is one way to quantify the Gibbs distribution is more like a local thing rather than a highly entangled thing. And in classical literature, like there is a 1-to-1 correspondence between the spatial decay of correlation and the mixing time of the Gibbs sampler. But one more thing I want to just clarify is so like when I say we have a Gibbs sampling algorithm or other people have a Gibbs sampling algorithm, it's more like a framework because how fast this Gibbs sampling algorithm, how efficient it depends on how you choose the jump operator. That's also very essential. So it's like the random unitary you're choosing will determines whether your algorithm is fast or not. And and I think in the hard case, the jump operator should be chosen in an ad hoc way for the problem you're working on.
Okay. You were asking about the usage of your algorithm for quantum Boltzmann machines. Throughout the workshop, and this morning also, and last night for y'all, there were talks about the contrastive divergence algorithm for training QBMs, and this can be described as you at least classically, you divide your Boltzmann machine. You can think of it as like two lines, right? So it's a kind of it's a 2D system, but it's kind of a trivial 2D system where there's like a line of what's called visible units and a line of hidden units. And there are connections between the visible and hidden units. And this contrastive divergence algorithm works by, you fix the state of the visible units, then you pick the hidden units at random according to the conditional probability of the Gibbs distribution. And for these local models, that factors nicely. And so that sampling can be done efficiently. And then once the hidden units have been chosen, you go backwards and pick the visible units according to the reverse conditional distribution. And you keep iterating this forwards and backwards. And what people find is that this works well in practice. And so we had some talks about trying to do this kind of thing in quantum. And I really wonder whether the approach that you're using could be useful for that kind of process.
So
Maybe, yeah, go
sorry.
ahead.
So what let me think. So the algorithm is like you fix some bits and get a new Hamiltonian and do a conditional sampling.
Yeah. So you have these like a classical Hamiltonian with tunable weights for the connections between the hidden units and the visible units. And at one step of this algorithm where you're trying to estimate a gradient, you do this forwards and backwards updates. And what it does is it replaces the role of preparing the Gibbs distribution or sampling from the Gibbs distribution on the visible and hidden units, because they say in the classical algorithm that even that is inefficient, even though we have this classical Metropolis. And so I think an interesting direction, I don't know if we can answer this right now, but I think an interesting direction would be, is there a way to modify your algorithm for this specific context?
Yeah, it sounds interesting, and I think it's very, very possible because I don't see any reason like why it cannot work. So as you asked before, like there's no restriction on choosing the jump operator, say.
Mm-hmm.
Yeah, like it's a very, very general algorithm.
Right. Yeah.
But like, have you ever? Sorry.
I just have a follow-up question. In classical contrastive divergence, there's this like nice interpretation of your conditioning on the visible units that maybe come from data, and then you sample from this conditional distribution and you go back and forth. Maybe it's not a question, but it seems hard to think of a quantum version of this where when you condition on the visible units, yeah, like what does that mean necessarily in the quantum case? Like,
I don't
how
know.
would you?
Like, do you condition on classical beats or
So for
quantum state?
classical contrastive divergence, that's how it works. But I don't know what the quantum version of
I
that would
mean,
be.
let me propose a quantum version.
Okay.
It might not be efficient. I mean, so you can add penalty terms to the condition qubits. So for example, you add a new Hamiltonian term such that if the bit is not zero, I mean, like it causes like infinite energy or very large energy, then this algorithm will favor to stay in the space, on the conditional space.
I see. Yeah.
But like I'm not sure this is the best thing. But
Would it not be that you would just so in Jiaqing's algorithm, there was this initial state phi that was prepared. Would you not simply replace that with the state of the physical qubits that you're trying to learn and you have sample access to?
Um, so you want so that phi is just the intermediate state in the Markov chain. I may misunderstood, like so when you say you put the state as input, what do you mean?
So what Eric was saying is in these classical algorithms, there's this data distribution that you're trying to learn. And that's over the visible bits. And so in this contrastive divergence, you just feed in for the initial step of the algorithm, the state of the visible bits. Right. And so classically, that's just some probability distribution over the visible bits. And so my guess would be you would just prepare the initial state of your algorithm on the visible qubits with the quantum state that you're trying to learn. I mean, it's just the
Yeah, sounds plausible. Like, but I think probably I should. Yeah, I might need to think more. Like, yeah, I might slightly misunderstood the dating, but it sounds plausible, and it sounds like an interesting question.
yeah, I think it would be very interesting for QBMs.
Yeah. I have a question for Jiaqing. So, like from the fundamental level or from your algorithm, do we know any relationship between the magic needed to prepare the Gibbs state and its temperature? Do we know anything about this?
You mean like
The
when
T count, for example. Yeah.
the T count? No,
Yeah.
we don't. Like you can analyze. So the first comment is, I think currently the algorithm is far away from like implementing on near-term quantum devices
I see.
because it's pretty expensive. So if
Yeah.
you read the paper, like I mean, it uses quantum phase estimation at every time. I mean, that's pretty expensive. Although I would think in practice you might not need do phase estimation to such high precision, and you can substitute the phase estimation with some more simple like method of estimate energy. Because I know some people like they are doing something similar and they are performing. Also, that's a few years ago. Like they are doing some kind of system bus interaction, and they implement those things on like the real devices. Conceptually, I think there are some connections. The thing I want to mention is like they are doing something very like not precise, but it turns out to be Gibbs state is more tolerant to like error. So
Okay.
it turns out to be the result is good. But like I think the T count will, if you analyze the current Gibbs sampling algorithm, no matter which one you're analyzing, it will be super high.
I see. Yeah, I ask a question because like I saw some papers like the Gibbs state, temperature, and the entanglement. So these kind of both resources. So I'm curious about this. Yeah.
Yeah, there are connection between entanglement and temperature. So yeah, there is a very cool results. Like people show that above a constant temperature. So but that constant is pretty high. Then the Gibbs state will suddenly become product state.
Okay.
Like, suddenly become like a mixture of product states. So like that's exactly zero entanglement. But in Germany, like the temperature when the temperature is too high, then it's product, mixture product. But when you lower the temperature, it will become more and more close to ground state.
I see.
Yeah, and there will be a phase transition. It's like a very sharp phase transition. Like as long as you're below this phase transition, it will be highly entangled. So similar, for example, like when you decrease temperature, when it's slight smaller than zero, the water will suddenly freeze. It's something like that.
I see. Okay. Yeah. So currently we don't know what happens for this kind of magical resource, right?
Yeah. Yeah, I think we don't know.
Okay. Okay. Thanks. Yeah. Okay, good. So any more questions? Okay, if not, the last speaker today is Lei Zhang. So anyone have questions for Lei Zhang? Okay,
Let
so
me ask.
yeah,
Oh,
you
I
ask.
have a question. So like how do you think about like imaginary time evolution in general? Like do you think there are fundamental limits or do you think it will work finally?
I think there are fundamental limits in terms of it depends on what property are you simulating. If you want to prepare the states from a fixed initial state, then it may not be a fundamental limit. But if we want to simulate the operator, essentially it's a non-physical one, and it relates to the exponential function, then it will be a limit of in terms of system size. If we assume the initial state is random, and further, I think it may be limited to the imaginary time if we consider the classical machine error. Because when we are simulating the exponential function, there are also classical limits to simulate them. For example, if like the time goes to 1,000, then it's really not possible to simulate e to the power of 1,000 in classical machine precision. So
Yes, I think I don't really understand when you say like the classical machine error. What does that mean?
It means that's when we need to simulate such transformation. For example, we use quantum signal processing to simulate the transformation. Then we need to firstly construct this transformation classically. For example, we need to construct this function in a classical sense. Then we use Fourier transformation, etc., to construct a Fourier polynomial that can approximate such a function.
So you mean the cost of block encoding?
Yes. No, the
Oh,
cost of calculating the angles for transforming such a blocking code.
okay.
Then that will be a fundamental limit when when the cost of simulating such exponential function increases. Well, when the time is lower than 50, it's totally fine, but it may cause a problem when it goes higher.
Okay. Thank you.
Cool. Good. Any more questions?
Hi, Lei. I've got a small question for you.
Okay.
So instead of consider simulating the entire, I mean the total linear brane dynamics, would you consider like focus on a subset of states, and you just need to simulate the action of the dynamics like regarding this subset instead of like any state?
It is possible, but we need to think about what state we are focusing on. And in that case, a general framework such as this may not be suitable anymore. For example, if the initial state is the identity, I mean the maximally mixed state, then the algorithm in this case may not be suitable to use QSP-based algorithm because they are for operators. So for initial states, different initial states may lead to different algorithms, of course.
Thanks.
Okay, good. Any more questions? I think yeah, the time is late. So if not, let's thank all the speakers today. Okay, and thanks for all these nice discussions and talks. Okay, I think that's all of today's session, and thank you all for the attention. Okay, and hope everyone will have a good 9-hour break, and looking forward to the next session. Okay,
Yeah.
so
Thanks to the speakers. Really very interesting.
yeah, very nice talks. Thank you. Yeah, see you.
See you later.
Yeah, see you.
Do you